The same analysis works even with objects that don't have contact. Here the force is contact force. Here we have two toy cars, let's say, with magnets. Okay, these are magnets, and they're opposing magnets so that they repel each other. The cars are approaching, and they exert equal and opposite forces on one another. So the car with mass 1 experiences force F12 exerted on it by the magnet of the other car, and vice versa. There's a force F21 exerted on the magnet of the second car by the magnet of the first car. Now, if the cars aren't going too fast, or if the magnets are strong enough, those cars will come to some proximity, but they won't touch. Come to some proximity and move apart. The delta T is likely to be much longer than it was up here, and I haven't actually indicated a delta T that looks much longer than this. But the same principle holds. You have force, you have time, you have a force versus time curve. You integrate the force with respect to time, and you get the change in momentum. In the same way, there's no difference. No difference in this analysis and this analysis. The key is that the forces are equal and opposite, and they're applied for the same time interval. And obviously, in a contact force, as long as they're in contact, the forces will be there, they'll be equal and opposite, and when there's no contact, they won't. So the time interval is the same for both. And the same is true here. The one difference, of course, being that there's really no limit on how far apart the cars have to be to experience a magnetic force. Theoretically, they experience a magnetic force if they're in different galaxies, although that force would be totally negligible. Magnetic forces drop off very rapidly, so without much error, we can just do a kind of a liberal time interval here and ignore the rest. The law is going to hold to any desired level of precision, accuracy. Okay, one other thing that I didn't do here. We're assuming that these are net forces. So I should put net down here. I don't have room to put net on these, but we're assuming that the only forces are the contact forces. If there are other forces present, that won't necessarily be the case, and it won't even necessarily be the case that the net forces are equal and opposite. So this is an ideal situation. I should actually put a net on the F average too, but that would get kind of messy. Okay, so again, what happens with these cars is they'll come to certain proximity, then they'll move apart. And after they've gotten to the point where the magnetic force becomes negligible, we'll say that's the point at which we'll measure the V1 prime and V2 prime. So if V1 and V2 are the velocities at some point where the magnetic force is negligible, they come together, they move apart. If these forces constitute the net forces on the two objects, then when the magnetic forces again become negligible, the cars will be moving with velocity V1 prime and V2 prime, and the change in the velocity of the first is going to equal F12 times its F12 divided by its mass multiplied by the time interval. Let me say that again. The velocity change of, well, actually, we're going to address velocity change. Okay, right now, let's just accept the fact that we have a force, that equal and opposite forces have equal and opposite influences on the cars, and that ensures that the impulse, the average force multiplied by the time interval, or alternatively, the integral of the force over the time interval, will be equal to the change in momentum. And we're also assuming here that the mass is constant. I was going to analyze the case of non-constant mass down here, Then I had the question whether that was in your textbook. It isn't, except as a challenge problem. So I'm not going to address that right now in an introduction to the conservation of momentum. So what we have here is two forces, contact forces, magnetic forces, with the same analysis.